What I'll be talking about is the partial fraction decomposition and how Matlab can be used to help conduct this laborious technique. And then from there we'll show you how the inverse Laplace transform can be found based on the partial fraction expansion. So here's a roadmap of what we're going to talk about. First, we're going to review with an example illustrating the concept of partial fraction expansion, as well as finding the inverse Laplace transform after we do the partial fraction expansion. And then I'll go into the Matlab command window to demonstrate how to solve the partial fraction expansion, and then find the inverse Laplace transform associated with the partial fraction expansion. And at the end, I provide a handwritten example of how to do the partial fraction expansion, and therefore we can see how Matlab can be used to verify our handwritten example. So here's an example of partial fraction expansion. Here we have a polynomial f of s given as s squared plus 6s plus 9 in the numerator, and s minus 1 times s minus 2 times s plus 4. And I'll show you in Matlab how we can multiply these roots of 1, 2, and negative 4 to form a polynomial, and that will be used to find the coefficients associated with the partial fraction expansion. And what I mean by partial fraction expansion is we put it in this form, where once we find the roots of the denominator, we want to express it as a decomposition of this function as follows. Because once you find this expression, you find a, b, and c, then you can use the inverse Laplace transform table to easily figure out what the function is associated with each of these partial fractions. So f of s will show where we do this example by longhand, but it turns out the results is that a is equal to negative 16/5 over s minus 1. So a is basically negative 16/5, b is 25 over 6, and c is 1/30. Now we find the inverse Laplace transform based on this partial fraction expansion, and we see that this is associated with the first term here. When we find the inverse Laplace transform, we know that's a function of f of t, and here it's just negative 16/5 e to the t. Similarly, for the second term, it will be 25 over 6 e to the 2t, and then finally we have 1/30 e to the minus 4t. So that's our inverse Laplace transform associated with this polynomial f of s. So basically we expanded to, in this case, we took this denominator that is third degree and decomposed it into single degrees or first degree in the denominator. And once we do that, we recognize the form of this, and we know it's an exponential, e to the t for this example, and e to the 2t for that example, and e to the minus 4t. And this was done on earlier videos. Now we note that f of s is simply, when we multiply the denominator, is s cubed plus s squared minus 10s plus 8, as well as the numerator being again s squared plus 6s plus 9, because we'll use this to show you how we take these coefficients and input it in Matlab. Now I'll introduce some of the Matlab commands to perform the partial fraction expansion, as well as finding the inverse Laplace transform. So here's our example that we did earlier. We define roots 1 with negative 4, 1, and 2. We form our denominator using the poly command. So when you do that, that yields a result of the denominator 1, 1, minus 10, and 8. We note that the numerator is just simply the coefficients 1, 6, and 9. And then we use the residue function, where r is the coefficients of a, b, and c when you do a partial fraction expansion for this polynomials, and k is the roots, and in this case, as you know, it's negative 4, 1, and 2. So we use this residue function, and it has input parameters of the numerator and the denominator that I defined earlier. Now once you get the partial fraction expansion, you can easily find, using Laplace transform tables, to find what the function is associated with this f of s. Another way to do the inverse Laplace transform is to first use the syms command, which basically symbolically takes these variables s and t and puts it in symbolic form. Then we use the inverse Laplace transform by this Laplace command. And here we just take this function in the numerator and the function in the denominator and express it as follows. So this would be s squared, s raised to the second power, plus 6 times s plus 9, that's our numerator, divided by s raised to the third power, s cubed, that's here. Then we have s raised to the second power associated with this term, minus 10 times s, with this, then finally plus 8. And that's it. And then we should get back our inverse Laplace transform associated with f of s. And now we're going to do the Matlab demo by going to the command window. Okay, let's input our numerator. Our numerator is equal to 1, 6, and 9. So this is s plus 6s plus 9. Now we have our roots associated with the denominator. As you recall, it's minus 4, 1, and 2. We can form a polynomial in our denominator based on these roots. And we have s cubed plus s squared minus 10s plus 8. Now we use our residue function. R will give us the coefficients a, b, c. K will give us back our roots. And then we use the function residue and we put our numerator and our denominator. What we have is the following. We get back our roots, negative 4, 2, and 1. Associated with the roots negative 4 is a coefficient of 0.0333, and I'll show you that's the fraction of 1 divided by 30. And then associated with the roots 2, we have 4.1667, and that's simply 25 divided by 6. And then negative 3.2 is associated with 16 divided by 5. And I'll put a minus just to be consistent, but you get the idea of how to calculate these coefficients. And we should get the same results shown here, here, and here. And that's what we have. So that's how you do the partial fraction expansion when you're given the coefficients of the numerator as well the coefficients of the denominator. Now one way to find the inverse Laplace transform is use the Laplace transform function, but we need to do this, convert the variables syms, the command, so we can convert this symbolically for s and t. And we use the Laplace domain, but let's recall what our numerator is and our denominator, and that's what we're going to use for this when we use the inverse Laplace. So Laplace. Now we're going to do the numerator, which is basically s raised to the second power plus 6 times s plus 9. We're going to divide that by s cubed plus s raised to the second power minus 10 times s plus 8. Close parentheses and close it for the function Laplace, and we should get our inverse Laplace transform that we did earlier. And we see we have our coefficients 25 divided by 6 associated with the root 2, 1/30 associated with the root minus 4, and minus 16 divided by 5 times exp t, which is associated with the root 1. So that's how you do, very simply, finding the inverse Laplace transform of a polynomial function s. The handwritten example for the partial fraction expansion can be found in the following YouTube video shown here. And that concludes this presentation on partial fraction expansion and how to use MATLAB.